All right, so welcome to the Graphics Programming Virtual Meetup. Today we will talk about this article, how to build a BVH. So bounding volume hierarchy. This is a data structure for ray tracing to be relatively fast. Otherwise, it's basically impossible to do it on a large scene. And this article will show how a proper BVH can be implemented without supporting libraries like DX or Vulkan or like optics. Put the link in the chat. So this article will discuss the basics, like what BVH is used for, or how a basic BVH is constructed or traversed with array. So it first starts from the background. The BVH is acceleration structure. It serves to reduce the cost of finding the intersection of array and the scene. Consists of just a lot of objects. And the basic principle is like BVH is divided by object. And there are also some other data structure divided by space, like octree. But for BVH, we do is like if we have 64 polygons, we split them into two groups of 32. Each group enclosed by a bounding volume. That's what the name of the BVH comes from. And then when intersecting with the scene, we can skip 32 polygons. And we do it recursively. So this is a visualization for that. I think this is like the BVH itself is probably not new to people here. But anyway, let's continue. We can define a triangle like this with 3 vertices and 1 centroid. I don't know what that is for, but probably he will explain it later. And we also have a ray, which is the origin direction, and t is the distance from the origin to the intersection point. So we can construct some random triangles. This into an array. And this array triangle intersection, which is the famous Moeller, I don't know how to pronounce that, intersection algorithm. And there are slightly fast approach, but yeah, this needs different data, so we will not talk about that. So intersection function determines if there is an intersection between a ray and a triangle. We will not go through this code. You can read the Wikipedia article or some other online sources, but it involves the barycentric coordinates. That's what those U and V are for in here. And if we do have intersection, we will get a t value, which we store inside our ray struct. So the t value for the ray will be updated. And we can also generate some rays. This is done by flying a ray from a camera position to a virtual screen. And we just do it in double for loop. I really don't like how when I click it, it becomes like this. Let's go back. Anyway.
Just reload the page and don't click.
Yeah, don't click on that. So yeah, and we have a nested for loop and then just shoot a ray. This is like basic ray tracing stuff, not the topic of today's article. So we will just not go through this code. We just assume it works. And now with a proper initialized primary ray, we can get our first ray trace view for the test scene by just brute force against the array triangle for each ray. And yeah, we can just use this intersect try function for that. And this is just a large value we use for the upper bound. And it means we hit nothing. We hit the background basically. And yeah, we get this picture. So yeah, for more rendering specific stuff, he will not talk about that in this article, like how to make lighting, how to make this thing looks pretty. There are a lot of books on this topic. So we will just focus on how to make this algorithm more efficient. So on his machine, it takes about 140 milliseconds to construct that many rays, and the intersected one is 64 triangles. That's not bad. We traced almost 3 million rays per second on a single core on the CPU. But however, the computation scale linearly with triangles, like 256 triangles takes that much time, and then yeah, more triangles takes more time, basically. So, I don't know that when the bounding volume hierarchy was first introduced, they assume that bounding volumes would be placed manually. I think some treated stuff still do that. Like, because you do SDF and it's very hard to have a bounding box for SDF, so people just place them manually. This is not something artists will enjoy. This is not something everyone will enjoy. This is what intern is for. Okay, so let's say, how BVH can be constructed automatically. We start by the scene and its bounding box. And there's a root node for the hierarchy. And then we recursively subdivide this node. And every time we just use a split plane and partition the primitive to two sets. Yeah, note that we do not split space because BVH is like object partition algorithm. And the partitioning is what we need the primitive centroid for. Yeah, I guess he just decided to pre-calculate that rather than calculating it on the fly. After the split, we have two groups of objects, and we can have the group bound. And the bounding volumes of two groups may overlap. That is totally fine. We just have two overlapping bounds. Yeah, so you can see the group here and group here are very far apart. So even if we intersect the left box, we still don't need to check those internal. So we need to deal with that. So for BVH, we need the following data. We need a axis aligned bounding box, A, B, B. This is the easiest to calculate and cheap to store. And yeah, a sphere is cheaper to store, but it's not convenient to work with, at least for ray tracing. Reference to two child nodes, and also reference to a primitive if it is a leaf. So it has something like this. And this struct has problems. First, it's large. And also, we just don't like the pointers and the stud vector because especially stud vector, it's variable size. And we can switch pointers to indices. And by doing that, we can even use the smaller indices, like just 8 bytes. And the primitives, we can store them in a huge stud vector, like all the triangles, and then just in the BVH again, we just store like the first primitive and primitive count here. Like a span or slice. Yeah, we can make several improvements to make this smaller because we will have a lot of those. Like the Boolean is redundant because primitive count cannot be 0. If it's 0, then it's not a leaf. Anyway, we can start to actually construct the hierarchy. First, we is to create a root node. For root node, we first pre-calculate all the centroid. And root node contains all the triangles, so it just the first primitive is 0 and the primitive count is everything. We call those two functions update node bound and subdivide. Update the AABB for root node is, we just run a for loop for that. I don't like they do extra work. Like what I will do instead then here is to construct the leaf node. After constructing the leaf node, then recursively update the bound upward. This way, I think it does a lot of extra work, but anyways.
How's the centroid used?
Centroid is used for splitting, so they're not there yet. So see here, we need a split plane. So we need like an x-axis or y-axis, and then we sort them, and then sort them by centroid, basically. Sort the.
Oh, okay, yeah, gotcha.
At least I think what he's doing, because there are more advanced algorithms I assume we'll be talk about in later articles, but this one just most straightforward one. Yeah, finally we recursively subdivide the root node. This is also like described in ray tracing when we can. I think, the process in that book and here is largely the same. We just determine the axis and position of the split plane and split the group of primitives into two halves, create a child node for each half, and then recurse into each of the triangles. So to split the plane axis, we just split the AABB along its longest axis. This one way, or in retracing in one can't, they just use a random function to select a random one. There are better ways, but we will not talk about it in this article. So yeah, we just calculate the extent of the whole AABB and then split the arc axis along the longest. And yeah, for split the group into two halves. And the combined size of the list of triangle in both halves are exactly the size of the unsplit list. And yeah, split can be done in place. We just do a partition basically from left to right. Yeah, he talks about partition also. Yeah, triangle do not need to be sorted. Partition is enough, basically. And then we create child nodes for each half. Yeah, the first child node contains primitive at the start of the array, and second contains the primitive starting at I. So we first create the child node indices because we use indices to represent the children. And yeah, we just do that. And theoretically, the split in the middle can yield empty box. He didn't deal with that. In retracing in when we can, there are some extra codes to check this. Also, we set the primitive count. We just split to 0 because it becomes like interior node. And yeah, we don't have this Boolean anymore. We use the primitive count to tell whether it's a leaf node or not. And we use this indexing scheme where the right child is always equal to left child plus 1. And that means for BVH node struct, we can further reduce another 4 bytes because we don't need to store the right child index. So the last question is, when does the recursion end? And oh, this is new to me. So when there is one primitive left is not optimal or not good, because two triangles often form chords. And if the chord is axis aligned, then we cannot split it at all. So we basically just, if we split them, we just have the two of the bonds to be exactly the same. But yeah, for this reason, we typically terminate when we have two or less primitive DNA. Okay, this is not completely safe, but for a solution, we need something else. So we will discuss later. And yeah, he talked about this code here. So this swap changed the original list of triangles. This may be fine if we own the BVH builder, but not great if we want to share it with something else. Also, swapping whole triangles by value can be expensive. So we can store a triangle index. Now a BVH node just refers to a slice of indices rather than triangles. So just like this. The index originally is just 1 to n, but then when we do partition, we just partition this index. The BVH node structure needs some updates. We don't store the index to right node anymore. We don't have this is Boolean. Instead, it is checked implicitly by the triangle count. Update bounds. We also need to use the indirection. So we still do the for loop, but we go through the indices and use indirection to get the original triangle. And yeah, this is the whole function, not that long. And then now let's talk about BVH traversal. Traversing it is a recursive process starting from the read node. We terminate if we miss the AABB of that node. Otherwise, yeah, if the node is a leaf, then we intersect the ray with the triangles. Otherwise, we recurse into the left and right children. Yeah, it's just implemented like this. We first intersect the bounding box. If it's not not hit, then we just return. Otherwise, we check if it is a leaf. If it is, we intersect for triangles. If it is an interior node, we recursively intersect the left and right. And intersect A, B, B is, we haven't implemented that. We need a slab test to intersect array with A, B, B. So the intersect BVH function does the work we previously did for with the loop over all the triangles. Comma operator. Oh, yeah.
Yeah, it's not too bad though.
So to be honest, I'm not even mad because like pair and tuple in C++ is so bad. So I can see why people don't want to use those, and they also want to group those two together. So it's just become this. Yeah, otherwise in here you need a like stud high, which is just ugly. Yeah, and this article postpones a lot of things. Like we can make the BVH node structure even smaller. And how to split plane axis and positions better than what we are currently doing. There is something called surface area heuristics. How do we safely terminate recursion in subdivide? And what about multi-threading? Most of the topics are for another day. But we can have a smaller BVH node structure. We currently have this. It takes 36 bytes, which is unfortunate because cache lines are like 64 bytes. So this unfortunately is not subdivided by 64. And we can reach the 32-byte node size when we realize that a node that has a triangle must be a leaf. It starts as no child node. And the other way is if there are child nodes, then there are no triangles. So we don't need to store a child node index and the index of the first triangle. Instead, we just can combine those two together. And we call it, this variable, how this variable will behave depends on the tri count. if try count is 0, then it contains the index of left child. Otherwise, it contains the index of the first triangle. All right, then this is the whole article. Stop recording.